Welcome. This video I'm going to derive the bohm sheath criterion, and this is a condition on the velocity of the ions as they reach the wall of any kind of confined plasma, and it determines the boundary conditions on things like fluid models that we use in the edge of plasmas. And so this is going to look at what happens when a plasma meets a conducting or a metal wall. So what happens if you have a wall like this, for example. I'm going to draw some kind of metal wall, and you have a plasma over here. The electrons and ions are moving around at their sort of thermal speeds. So thermal speed. So if electrons and ions are moving around, the electrons move much faster than the ions, and so the electrons will reach the wall first. And what will happen is that as electrons and ions reach the wall, to a good approximation, they stick to the wall and recombine into gas, and so they're lost from the plasma. And so as the electrons reach the wall first, the wall charges up relative to the plasma, and an electric field forms. And the electric field is in the direction where it repels the electrons and attracts the ions. So you get an electric field like this into the wall. And this is formed because you have a region of the plasma where there are fewer electrons than there are ions, because the electrons have left and hit the wall. And this electric field which forms repels the electrons and pulls in the ions. The electrons are now reflected back from this electric field, and the ions, which have a slower thermal speed, so the ions come in, these are accelerated and into the wall. And this electric field gets bigger until it reaches a point where the electron flux matches the ion flux. So at some point we have a small amount of electrons getting through, and this matches the flow of ions to the surface. And so the electron and ion flux balance, and there's no net current. And so we reach some kind of a steady state. And so we can draw the potential and the densities. So what happens here is that we have if I draw this as this distance here is x, with the wall is here. And I can draw now the different densities. So you have this like density n. So in the main bulk plasma, the electron and ions have the same density, but when they reach the wall, the electrons leave first, or fastest, faster than the ions, as the electron density looks something like this. The ions, so over here the electron and ion densities are very similar, but the ion density drops less quickly. And so in this region here, these are the ions, and so these are the electrons here. This is electron density. And so what's happening is that we have a space charge region here, which is positive, and the wall is negatively charged relative to the plasma. And so there's an electric field, and the potential is increasing in this region here. Now this region where the electron and ion densities are not equal, this is called the sheath. And this has a width which is a few Debye lengths, because the plasma shields out electric fields and shields out any differences in electron and ion density on the order of this kind of length scale, where lambda d is this Debye length. So square root, we have an epsilon naught electron temperature, and an NE. Well, this is the density. In fusion plasmas, this is of order micrometers. So if you put a few electron volts into here and 10 to the 19, 10 to the 20 or so into there, you'll get of order a micrometer or so for the lambda d. And so there's a very narrow layers near the edge of the plasma, and so we can make several assumptions to try and find out what's happening here. One is that it's just one-dimensional, because I'm just drawing everything here as a function of x, which is the distance to the wall, and because these are such thin layers, they really only notice the direction perpendicular to the wall, because they're so thin compared to the variation in the curvature of the wall. And so we can treat them as one-dimensional. Because they're so thin as well, we can usually treat the temperatures as constant. So the electron and ion temperature as being constant across this very narrow region. Again, because if there was any temperature gradient, it would very quickly be cancelled out by the motion of the charges, motion of the electrons particularly. And so, yes, so these simplifications allow us to work out essentially what the sheath looks like. And we can work out first the electric field. So to do this, we use this equation. So we have the charge, epsilon naught. So this is the charge density, which is just the difference in the ion and electron densities. So Ni minus Ne. And most of the time in plasmas we assume these are equal, but here we can't, because in the sheath this is what's really driving the electric field. And then here we assume the electric field is, because it's steady state, E is just minus grad phi. So steady state, so there's no there's no electromagnetic component, and so this just gives us in one dimension we just have that minus d2 phi by dx squared, which just come from this, is just equal to E Ni minus Ne epsilon naught. So this equation will tell us what the potential is, and so we'll end up with a potential which is kind of increasing as you go from the wall into the plasma, because the ion density here is higher than the electron density. But we need to know what these are, so how to calculate these. Now there are several ways of doing this. So we'll start with the electrons. And so we can start essentially with the either Ohm's law or the electron momentum equation, which gives the same thing. So we have the E electron velocity cross B. So this is just writing down electron momentum equation essentially. So we're going to cancel out a few of these terms. So first of all, we're going to ignore the magnetic field. So we're going to say it's unmagnetized. We're going to then also assume it, because it's steady state, we can get rid of this d by dt term, so the electron momentum term. And the advection components of this we can get rid of, essentially just assuming the electron mass is small. And so we just have a balance between the electric field and the electron pressure. And because we're at such a thin layer, we assume that Te is constant. And so the electron pressure, which is just E times N times Ne times Te, this we can just take the derivative of the temperature outside, the gradient, and remember the E is just minus grad phi, so minus d phi by dx from the electric field, equals, here we just take the T and the E outside, so we have a minus Te over N, and then just left with the Ne by dx on this side. So this relates the electron density to the potential, and actually we can integrate this in both sides. Integrate this up here, so we have so the integral of d phi by dx. We're going to integrate that in dx, and then this gives the integral of Te over n, so Te is constant, dn, and this of course just gives the log. So this is the Te times the log of n, and this gives the change in potential from the wall to wherever you are, whichever location it is. And so we can write down the equation here for the density, where here the S means that the sheath edge, so these values here refer to the potential at the start of the sheath, so this location here. So here we have, at this location here, we have Ns and potential phi S. We assume at this point that Ne equals Ni, and both are equal to Ns. So this is the sheath entrance. And then using this formula here, we can relate the density at any other point to that sheath density, and the difference in potential. That's just come from integrating this here. So when we're at the sheath, this is equal to 0, and we just have that Ne is equal to Ns. As the potential drops, we end up with smaller electron densities in the sheath. So we're going to come back to this formula. So that gives us the density for the sheath, the electron density in the sheath, and this is just the Boltzmann. So now the ion density, we need to look at the ion momentum equation. So ion. So here we start with the momentum equation. So we have this here. So as with the electrons, we can now cancel out some terms here. So it's steady state, so that can go. We can then, here we're assuming this is collisionless, so there's no, so we can get rid of this term here. It's a bit of an approximation as well, but for now we can remove that. We're also assuming it's unmagnetized, so the magnetic field goes 0. Unmagnetized, and so we just end up with these terms involving the advection, the ion pressure, and the electric field. Now what we can do to simplify this even further is we can drop this ion pressure term, and this is assuming that the ion thermal speed is small. So here we're assuming cold ions. This works surprisingly well even for reasonably hot ion situations, because as we'll see shortly, the ions are accelerated into the sheath, and so the ions end up with a very large net motion, and so their thermal speed is actually smaller than their drift speed. So there's a correction to the sheath criteria that we'll derive when you have finite ion temperatures, but the same form of the equations still occurs. So this actually can be neglected and can still give a very good answer. But it's because the ions are being accelerated to high speeds, and so they have a net flow, and their thermal speed can be neglected in many cases. So I'll write it down, this equation in one dimension, so the gradients just become d by dx, and again E just becomes minus grad phi, and so we just end up with this. So you have mn, you have a ui, which we're going to call just in the x direction and drop the vector, so it's dui by dx. And on the right hand side we have a minus en d phi by dx from the electric field. Then we can integrate some of this up, so this is ni here. This part is right as a half, and then d by dx of ui squared. And here we also have an ni, so here of course the ni's can cancel. So those n's cancel. We've got something which looks like a half m times a u squared. This is basically a kinetic energy. And we have an E times a potential. So this is a potential energy. And this is just giving us conservation of energy. So I have that d by dx of the half, and then mi ui squared. And then move this over the other side, so we have a plus E times phi. So that's 0. So it just says that this here is constant. So this brackets, this is constant. And so we write down that the ion velocity at any point and the electron potential, or the potential at any point, are related to the sheath entrance values. So we can write down. So then we rearrange this equation and just put make the subject this ui. So we put that on the left hand side. So it's just the ui, and we take out a factor of us. So we end up with a us here, square root. Now we've got a 1 here, and then on this side we end up with, we've moved over phi s minus a phi. So we end up with here with an e at the factor of the front. We then divided through by m and multiply through by 2. So we end up with a factor of 2 here and an mi. And then, because here we've taken the square root of this, so if we square it again, we know the us squared here and a ui squared here. At this point here we need to cancel out this us, we need a us squared here. And so this expression tells us how the ion velocity changes as a function of the sheath ion speed. And we can then combine this with the continuity equation. So we have, if we have conservation of particles, so there's no ionization or recombination, anything like this, then we can write down the ion continuity equation. So we just have divergence of NiUi, and since it's steady state, that goes to 0. And so we just have that this is just says that the d by dx of NiUi equals 0, and so this is constant. And so we just write down, using this relationship here, we can just write down that the velocity at any point, the density at any point is just the sheath density, and then it's just 1 over this quantity here, because these two multiplied together must be constant. And so we end up with this 1 minus, just makes it look a bit better, so phi minus phi s over us squared I, and that's all now to the power of minus a half. And so this gives us an expression for the ion density, and that we can combine with the electron density above and Poisson's equation, and we can put them together to get an equation. So this is putting into the equation like this. So we have, so this was the charge, so E Ni minus Ne over epsilon naught. And if you put in this Ni value here and Ne from the previous, from the Boltzmann, then we get this expression here, where here this is the ion density component and that's the electron density component. It's then useful to normalize these equations to make them easier to manipulate. And a good choice for this is that we have a normalized potential, which is, here we just flip this to minus phi s over Te. So this is a normalized potential, normalized to the electron temperature. We have a normalized distance y, which is like a square root 2 times the x direction over lambda d, where lambda d is the Debye length again, and we define a constant k, which here is miu I squared 2 e times electron temperature. So E times Te is in joules, it's the thermal energy, and a half mu squared is the kinetic energy. So it's like ratio of ion kinetic energy to electron thermal energy, and this gives an equation. So this gives a normalized equation for the potential phi, which is a non-linear equation, so it doesn't have an analytic solution. We can integrate it and then show that this does give the Bohm criterion. So you multiply through by d phi by dy, and you integrate. So integrate in y, and it gives this equation here. Now this is also a nonlinear equation and impossible to solve, or very difficult to solve analytically. Usually has to be solved numerically, but it does have some useful features we can use to actually calculate a condition on the flow. The main one is that this has to be greater than or equal to 0, because otherwise this will become imaginary, and that is essentially what leads to the Bohm criteria. So we have to make sure that this whole expression is larger than or equal to 0 for all y, and so the easiest way to do this is to expand for small. So for small capital phi, so this is when the potential is close to the sheath potential. So this is where you're near sheath, sheath entrance. That's where phi goes to 0 at the sheath entrance. And so you do a Taylor expansion of these terms, and what you get is this. So here I've expanded the exponential here, e to the minus phi, as this term here. So this exponential becomes this part here, and this term here has become this expansion down here. And then we can cancel out some of these terms. So here we just find that the zero order expansions, the ones here, all cancel. And as to the first order one term, so you have minus phi here, and then cancels with this, so you have a half 1 over 2k, cancel with 2k, so here we just have a plus phi, and so these terms all cancel. Do that one, cancels with that one. And so what we're left with is a term, so half phi squared, so the second order terms, so these don't cancel. So we have some second order and higher order terms. So this gives basically a half phi squared and takes the factor outside the front. So that's this one here. Then we have a minus, so we have a 2, so that cancels part of that, so we get a quarter. I'm taking out another factor of 2 here, so we have a 1 over 2k. Plus anything of higher order, so we have higher order terms. So terms which are of order phi cubed and higher order terms. These also turn out to be positive, but to make sure that this is positive, so remember this must be greater than or equal to 0. The main thing is to make sure that this part here is positive, so phi squared is positive here. And so k must be larger than a half. So k is greater than or equal to half in order for this to be positive. And if you look back at what k was, so k here is mu squared over et, so this should be bigger than a half. And so we have that miu I squared over 2ete must be bigger than or equal to a half, and that means that the thermal velocity of the ions, so the drift velocity of the ions must be bigger than or equal to the square root of ete over mi, and that's the Bohm criterion. And so what this says is that the ion velocity at the sheath entrance, this is at the sheath, so it's really sort of US. So this is the sheath velocity of the ions must be bigger than or equal to this thermal speed. And so what it says is that if there's a valid solution, then when the ions come into this region here, at this point here the ions are moving, so US here is square root of ET over MI. So they're moving at the essentially local sound speed. And so the ions are accelerated into the sheath and are going at sound speed at this point. And that means there must be something in this region to accelerate the ions, because far away from the sheath the ions are essentially stationary. And so between the sheath and the main plasma there is a region called the pre-sheath, in which there's an electric field which accelerates the ions so that when they enter the sheath they're going at the sound speed. And this is the pre-sheath region, which is much larger than the sheath itself. So there's a pre-sheath with an electric field, but with Ni approximately equal to Ne. At the sheath entrance, the ions are going at the sound speed, and then inside the sheath, the ion and electron densities are different.